Okay, so today we're going to be talking about redox reactions, but more specifically talking about the application of redox reactions. I know I had you going through the notes and how to balance the redox reactions. Now, I'm going to probably make all of you very happy that you really don't have to do many balancing like that, because we're not going to see very many reactions with the oxygen, so you don't have to add the water and then the acids, and for most of the time they're actually going to be done for you. We're just going to apply it. So hopefully you reminded yourself that to know oxidation, you're losing electrons, which means electrons will be on the left side of the arrow because they are being taken away. That's how you're forming a cation. The oxidation number becomes more positive. Whatever you have to say to put it in your head that you know oxidation is losing the electrons, then reduction is gaining the electrons. It becomes more negative. The electrons are on the left side of the arrow. Let me practice my rights and lefts again. So electrons are on the right for oxidation because you're being lost, and the electrons are on the left for reduction because they're being added or gained. So galvanic cells, this whole unit is about transferring the electrons. Something's going to lose, something's going to gain. But a key thing to remember is that you have to lose and gain the same amount of electrons. And from a flow of electrons, that's where we get electricity. We're going to be talking about batteries. So we have two types of cells. The galvanic cell or a voltaic, know these mean the same thing. You can see them written both ways. You need to recognize these are the same thing. This is a spontaneous or thermodynamically favorable, yes, that's still around, cell. This is when you have a positive cell. This is a battery. All those key words and clues of what kind of cell. Electrolytic cells then are non-spontaneous cells. You're going to have to add some kind of power source because the reaction doesn't want to happen, so you're going to have to force it to happen. Today we're just talking about the galvanic cells. Okay, so there's a lot of the vocab, and the big thing with this is you have to have the vocab straight. So it's talking about the movement of electrons. So very common way a galvanic cell will look is you're going to have two separate beakers. Okay, this is one way, or another way, right here, they've separated it from a porous disc, but somehow you have to have two separate reactions. That's like a huge clue that it's a galvanic cell. The other thing you're going to have is a salt bridge. All galvanic cells have to have a salt bridge. We're going to talk about all these components. This is for the flow of ions. The purpose of a salt bridge is to balance the charges. If you do not balance the charges, the battery won't work. Again, I'm going to show this in more detail. The wire, okay, electrons flow through the wire. A very common AP question. Draw the flow of the electrons. We're going to talk about how they flow from anode to cathode. The electrons flow through the wire. Do not have electrons traveling through the salt bridge. Ions travel through the salt bridge, not electrons. So you will literally just draw the electrons, and then you're going to draw an arrow of which way those electrons are traveling. Don't have electrons floating here. Like, oh, I'm not sure. They might be here, they might be here. They're not going to give you maybes. Put them up above the electron of which way, or the electron up at the wire, which way are they flowing. So the other thing, okay, look at the, let's see, salt bridge. This was I think on last year's test. What's missing in the diagram? And the salt bridge was missing. Salt bridge balances the charges. Okay, so here's our vocab. Anode. The anode is where oxidation happens. Always. Always. I don't care what cell. Put that in your brain. That's another thing that has to be tattooed. You have to know the anode is where the oxidation, so therefore at the anode is where you're losing electrons. So typically if you're losing electrons, look at what's happening. You are going from the solid and you're going to go to aqueous. Paying attention to the states can also help you to recognize what's going on in a cell. Because this is the solid, we're going into the solution. Both of these have to be in there. You have to have the iron and the solution. So anode is oxidation. Cathode then is where the reduction happens. And in all of electrochemistry, you have to have an oxidation and reduction. Redox stands for reduction oxidation. We don't have a re-re or an ox-ox. That doesn't happen. You have to have both. So look at what's happening. The copper is going to gain an electron to form the copper solid. So this is your solution, which should have a charge, so that'd be a copper plus 1, is in solution becoming a copper solid. So look at what's happening in terms of the mass. So an anode, you're forming more solid. Cathodes are where you're forming more solid. So the cathodes are going to typically gain mass. Anodes, we go back, anodes, you're going from the solid to the solution, so therefore an anode will lose mass. So, okay, so let's look at this picture of what a cell is. So let's look at all the different parts. Okay, look at the electrons are traveling, and look at the mass over here. So if we can look a little bit closer. Look at the zinc is going to a zinc plus 2 ion. You're losing electrons. This is the anode. And look what's happening to the anode. Those zinc solid are gaining, they're losing electrons. So since they're losing electrons, you are seeing an increase in the concentration of the zinc solution. Okay, look at what's happening over here at the cathode then. The cathode is where you get reduction. So those electrons that came from the anode are reacting with the copper ions that are in solution, and you're going to see more copper solid forming. So that is why the cathode will gain mass. The anode tends to lose mass. Okay, let's look at the salt bridge. What's happening over here if we talk about the cathode? So in the cathode, since you are losing positive ions because the copper ion is going to copper solid, so you are getting a reduction in the positive charge in the cathode. So you need to balance that the positive charge. So what happens then? The potassium, the positive, it's not always potassium, so the positive is going to go to the cation. Oh, but you know what? What is the name of the cation? I just said it. What's the name of a positive charge? It's the cations. So look at the cation flows towards the cathode. Cat to cat, cat to cat. So look at what's happening again if we look at the zinc. In the zinc, you're adding more positive charge to the beaker. So now I have too many positive charges on the anode side. So to help balance the overabundance of positive charge, you're going to get anodes, or anions, flowing to the anode. So anions, the negative, flow towards the anode. So an anode has oxidation. An anode will lose mass. An anode, this is called the electrode. So the anode electrode loses mass. An anion from the salt bridge will flow through, the salt bridge will allow them to move. The anode is being replaced of ions from the anions. Cathode, reduction, gains mass. Cations flow towards the cathode. Electrons, look at the electrons. Well, just if you think of the order, well, oxidation's losing, reduction's gaining. That's why the electrons flow from the anode to the cathode. Now, a common question, the zinc has lost mass. Where is that mass going? Do not say the mass from the anode is going to the mass of the cathode. What's flowing from anode to cathode is the electrons. We know electrons doesn't have very much mass. The mass from the anode is going into the beaker, into the solution. So if we had a scale on this anode beaker, it wouldn't be changing mass, because really the mass is just going from the solid into the solution. Same thing over here. The mass is going from the solution into the solid, so you're not seeing a change in this cell, but you do see a change in the overall electrode. So let's kind of sum up what that was kind of looking at. And we have sayings. So an ox and a red cat. And we've actually changed this a little bit more. You don't have just a red cat. We have a big fat red cat. So we have a fat red cat. Why do we have a fat red cat? Because red cat means reduction is the cathode, and it's fat because they're the ones that are going to gain mass. So that's why you have a fat red cat. And then we have an ox. An is for the anode, ox for oxidation. But we don't just have an ox, we have an anorexic ox. I can't spell anorexic. Anorexic, whatever, you know what it is. Anorexic ox. I tried to Google that and I got some really disturbing pictures. So you're going to have to kind of decide your own anorexic ox. But again, why is he anorexic? Because he's losing mass, because the anodes will lose mass. And again, electrons travel from the anode to the cathode. They always go from anode to cathode because you are going from losing what's happening at the anode. It's oxidation. What do oxidations? They lose electrons. Where are those electrons going? They're going to the cathode because what happens at the cathode? Reduction. What is reduction? Gaining electrons. Where did those electrons come from? They came from the anode. But that's why they flow from the anode to the cathode. Okay, you can think of it alphabetical. They go from A to C, or you can think of it just in terms, losing and gaining, whichever way that you know which way does that electron flow. Common question. So again, looking at this picture, this is where it's a little bit not moving, but look at what we know. So in this, if this is the anode, what's happening at the anode? So to write the half equation, zinc solid is becoming more zinc ions because it's losing 2 electrons. So that is the oxidation half. I know that because it's the anode, and at the anode, oxidation happens. Here's the cathode. What happens at the cathode? It's reduction. So copper, the copper, and it's a +2, I know that, is going to gain 2 electrons, therefore to form the copper solid. So when we have the cell, you have to have a zinc, but it has to be in a salt of the zinc ions. So I would put zinc in it could be a zinc sulfate, zinc chlorides. We're going to have something spectating. Then again, this is a copper, same thing, and a copper sulfate, some kind of solution, and a copper and copper electrode. Look at the electrons traveling through there. This would either be porous, or we would say we need a salt bridge to balance the electrons. Now, a salt bridge can be a piece of filter paper, somehow that allows the movement of the liquids. Okay. So the voltage, so if you look at back here, this is also a key thing that we can tell it's a galvanic cell. This is a voltmeter. It's reading the voltage across. This is where the batteries come from. A 9-volt battery would be having a 9-volt potential difference between the two cells. So if you see a voltmeter, you know it is a galvanic or a voltaic or a spontaneous cell. Okay, so this is where the calculations come. We're going to calculate the E cell potential. potential. What you need to know, E cell positive, this is spontaneous. E cell positive, it's a galvanic or a voltaic cell. So a positive E cell means it's going to have a negative delta G, and yes, we are going to relate those. Okay, it's going to be a volt. Now look at a volt. This is also where we have to be careful. A volt is a joule per a coulomb. Okay, but this means a joule, so when we do some math with the delta G, we're going to again have to be careful of our units. So to calculate the E cell, this is what you need to know. You're going to take the cell from the oxidation and add it to the cell of the reduction. These are not numbers you will have to memorize. They will give you these on a reference table. So in fact, I have it printed for you. If you haven't had a chance to pick it up, I can tell you in the book, it's page 873. This is what it looks like. It's on page 873. This is where it's actually kind of annoying, and it's gotten better on the test. They used to give you this entire thing, but now they only give you a much smaller portion of what is relative to the question. So look at this. So the higher the cell voltage up here, the more it wants to be reduced. So if you look at all of these, and they will always be written in reduction. Okay, it's always in all of these are being reduced. All of these are being reduced. Here are these ones I talked about that were going to be balanced. So if you look at the ones that have the hydrogens and the waters, those are in the acidic solution and they've already been balanced for you. The half has been balanced. So the thing is we need to have some of these oxidized. So you will be reversing one of these. When you reverse it, you have to change the sign. So oxidation, reduction. So when we're looking at this, the oxidation is the one that was reversed. They're not going to give that to you. So the standard cell, we're just adding oxidation and reduction. Now, again, everything is typically at standard conditions. 1 atmosphere, the 25, and a 1 molar solution is standard. Next class we'll talk about what if it's not standard. So for right now, everything's at a standard condition. Okay, so looking at that, you do have to change one of the signs. You are going to have to see which reaction is being oxidized and which one's being reduced. That's why oil rig, Leo goes grr, whatever in your head, you have to be able to recognize is one being reduced or what's being oxidized, because that's going to answer what's at the cathode or what's at the anode. Now, if you looked on that chart, there is the 0 is the standard hydrogen potential. This is your neutral. So everything is compared based off of the comparative to the hydrogen cell. And again, they're going to give you a much smaller chart, but this is what the standard hydrogen potential. A lot of times they'll use a platinum electrode. And the reason they do that, because platinum is very non-reactive. And so if they ever use a platinum electrode, that means ignore it. That they're using it so they can actually have the rest of the cell going. So the more positive the reduction, that means they want to be reduced. Those are the ones that are always going to be reduced. They're going to cause the other ones to be oxidized. We don't really have to worry about the agents. So what you just have to do, you're going to look at these numbers, and we know we have to change the sign of one of them. When if we look at it, so you're going to change the sign. That's going to be, when you add the two together, it's still going to be positive. The one thing you have to know, this is not Hess's law. Not Hess's law. So you will not multiply. If you have to multiply it by 2 to balance the electrons, you do not multiply the E cell. The only thing you will ever do to those E cells is change the sign and add them together. So if you look at the way it's written, and if it gives you a positive cell, you say it is spontaneous. If it's a negative cell, it's not going to be spontaneous. Electrons will flow in the direction that's going to give you a positive cell. That's how a battery works. So let's kind of look at this. If I have these two, look at these two possible ones. So it would be, okay, how am I going to combine these to make it spontaneous? You're going to have to make something be oxidized. You can't have oxidize or reread this way. So look at the two possibilities. We can change. We flipped in this one. Look what we flipped. We switched zinc. So in this case, this is where, oops, that arrow should have gone all the way over there. Zinc was being oxidized. And look what's happening. Copper's being reduced. So that meant in this one, we would have kept copper. The E cell for this would have been copper at the still positive 34. But you switched the zinc. So zinc was a 0.76. So this is a 1.1 volt cell. This is going to happen because the E cell is positive. This way, copper was being oxidized, so that meant we were changing this cell. So in this case, the oxidation part was a negative 0.34 because I reversed it, so I reversed my sign. You kept the zinc being reduced because zinc is being reduced, which is a negative 0.76. This gives you a negative 1.1 volt. This is non-spontaneous. That's not going to happen. Okay, so what's going to be our spontaneous reaction between these? You're going to have to turn one of those. So notice the two things. I want to know you're going to have to know the balanced equation, and I want to know the cell potential. So let's figure out first which one we're going to have to reverse, which one's going to have to be oxidized. So look at your cell values. If I reverse the manganese one, you're going to end up with a negative 1.28 volts. That's not going to work. So we know that we're going to make the chromium be oxidized. So chromium plus 3, that had to be oxidized. So we kept the manganese as it was. All I'm doing is rewriting it. Plus 2 waters. Okay. Now, still with balancing, to write the overall equation, we have to equal out the electrons. And so I know this. What did I do to it? I changed it. So this is my oxidation. So my oxidation is a positive 0.74. This is my reduction. I didn't do anything to it. It's a 1.28 volts. Okay, now you have to balance electrons. So this is where 3 electrons 2. So I'm going to multiply this one by 2, this one by 3. So when you multiplied it, so we multiply this by 3. What does that give us? 12. That's 6. That's 6. So that's 3. That's 6. Okay, here comes a test question. What's the total mole of electrons that were transferred? Right here is where you get that answer. 6 moles of electrons were transferred in this reaction. 6 moles of electrons. So then you're just going to cancel everything out. Okay, so we've done that. So there's my overall balanced equation. And now what you do, just add the voltages together. Okay, do not multiply the voltages. Notice I do not multiply this. Even though I multiplied this one by 2, I multiplied the reaction by 2, do not multiply the E cell by 2. I multiplied this by 3, do not multiply the E by the voltage. Just add them together. So it's a positive voltage. That's what you wanted for a galvanic cell. Here's your balanced equation. You transferred 6 moles of electrons were transferred in that reaction. Okay, typically, now here's a typically you're going to see the cells, anodes on the left. Do not count on that. Do not, do not, do not count on that. So make sure, I would probably even get in the habit of writing them the different way, so you're just not automatically looking at the left side and saying, that's the anode. It's not that. In fact, more and more test questions, I'm seeing them mix it up because of that. They don't want you to memorize. So if you look at it in the packet, pages 7 and 8, I just want you to practice on that. We're not going to talk about non-standard or the Nernst equation or anything today. This again could be an easier unit. We've really kind of just finished galvanics, and so we're going to spend some time next week looking at them and playing with them and doing more practice with these kinds of problems. I will see you next class.